Hi, my name is Gabriella Hod, and I'm doing my video presentation for the strain Rosette problem. Okay, so the problem states that the strain rosette shown is used to measure the strains on a structure made of 6061 T6 alloy aluminum. Gauge 1 reads negative 150 times 10 to the negative 6 inch per inch. Gauge 2 reads 400 times 10 to the negative 6 inches per inch. And gauge 3 reads 250 times 10 to the negative 6 inch per inch. Find sigma 1, sigma 2, and the max shear stress. And it says to report your answers in KSI and to explain Moore's circle. And so I've written down the information that was given in the problem. This is the strain rosette that is shown in the example. And originally, the strain rosette in the example is shown where gauge 2 is on the x-axis, but I'm going to change it to make what I think is an easier way of solving the problem. And I'm going to make the first gauge on the x-axis. And so I will turn it so that this is gauge 1. It goes 75 degrees until it hits the second gauge here, and then another 75 degrees until the third gauge right here. Okay, so now when solving for a strain rosette problem, you want to find the strain of X, the strain of Y, and the shear strain of XY. And so this is the first thing we're going to solve for because we want to get our state of strains first. And so to start off this problem, when you're doing strain rosette problems, you use these equations. And since it's given by gauge 1, 2, and 3, I'm going to write the equations as strain 1, strain 2, and strain 3. And so the equation is going to be the strain of X cosine squared theta, and it's going to be, the theta is going to be the angle of the first strain, so it's going to be theta 1. Then we have the strain of Y multiplied by sine squared theta 1 plus shear strain of XY cosine theta 1 sine theta 1. And this equation is going to be the same for the strain of the second gauge and the third gauge. The only thing that's going to change is the angle that's being used. So the angle that's going to be used for the second and third one are the angles for the second and third gauges. And so I'm going to rewrite it for the other gauges. And so gauge 3 is going to have strain of the third one. Okay. So from the way that I made the orientation of this strain rosette change, since we have gauge 1 here, and it's on the x-axis, we can already determine that the strain of X is going to be whatever value the gauge 1 reads. And so I'm going to write that down here. I'm going to write that strain of X is equal to, and we wrote down from the problem that gauge 1 is negative 150 times 10 to the negative 6 inch per inch. And so that's going to be our first value that we can use and plug into these equations. In order to get the other values of the equations because we also need to still have two unknowns, which are the strain of y and the shear strain of xy. We need to also know what the angles are for each of the gauges. And so I'm going to write the angles up here. So by looking, since gauge 1 is on the x-axis, the angle for that is just going to be 0. For gauge 2, since it is 75 degrees from the x-axis, the angle is going to be 75 degrees. And for gauge 3, since it takes 75 to get to gauge 2, and from gauge 2 to 3 it takes another 75, we add these two angles, and so we get 150 degrees for gauge 3. And so now we are going to plug in these angles into these equations in order to solve for the unknowns that we have. And so I'm going to start off by doing this equation right here for the strain of the second gauge. And so we already have this value here. I'm going to underline it. But so for the second gauge, we have strain of the second gauge equals, and that equals from the problem 400 times 10 to the negative 6. And then that we already have we discovered that the shear, or the strain of x, since it was also given the problem, we can just plug that in. So negative 150 times 10 to the negative 6 times cosine squared, as from the equation. Theta 2, we just found from the image, is 75 degrees. Right, the strain of y, sine squared, 75 degrees, plus the shear strain of xy, cosine 75 times sine 75. And then what we're going to do is we're going to take this portion of the problem and subtract it from both sides. And that will, let's find out what that gives us. Or sorry, add it to both sides since it's going to be negative, so we're going to add it to this side. So we have negative 150 times 10 to the negative 6 multiplied by cosine of 75 squared, and that's going to be added to 400 times 10 to the negative 6th. Okay, and so from that we get that the answer that this side of the equation is going to be 4.10048 times 10 to the negative 4. And so that's just this portion. If we solve for, so now equals the strain of y, and sine squared of 75 is going to be .933, and the shear strain multiplied by cosine 75 sine 75 is going to give us 0.25. And so this is our first equation that we get from this, and we can't really get anything from it because we don't have anything to substitute in yet. And so now let's solve for the third gauge. So we have the strain of the third gauge, which is given as 250 times 10 to the negative 6th, equals e to the strain of x, which is also given in the problem, multiplied by cosine squared. Now we use the angle of the third gauge, which is 150 as shown here. And so we put that in, plus strain of y, sine squared 150, plus shear strain, cosine 150, sine 150. okay? And from there, we do the same thing where we take this portion, and since it's negative, we add it. We're going to add this to this side of the equation. And when we do that, let's see what we get. So we get 3.625 times 10 to the negative 4 equals, and then if we solve for sine squared of 150, we get that we still have the strain of y, but it's going to be multiplied by 0.25 because that's what sine squared of 150 is, plus the shear strain, and that's going to be multiplied by, we solve for cosine 150 times sine 150. That gives us negative 0.433, and that gives us the next equation. And so from there we now have two equations, and we have two unknowns. And so in order to figure out what these two unknowns are, we can set one equation equal to either strain of y or the shear strain of xy, and then plug that equation into the other one. So I'm going to take this first equation and I'm going to set it equal to let's set it equal to the strain of y. And so that the strain of y would give us, so we have this on this side, so we're going to subtract shear strain xy times 0.25 and then divide by 0.933. So we have this minus shear strain times 0.25 divided by 0.933. And so now that we have something that the strain of y is equal to, we can now plug this into our equation for gauge 3. And so we have the 3.625 times 10 to the negative 4. And then we have, it's equal to, let's do 0.25 from here, multiplied by the multiplied by the strain of y, which we just set equal to from the other equation, so we're going to plug this in. And then bring down the rest of the equation. So we can solve for what's inside and then distribute the 0.25. And if we do that, let's do that really quickly. So the 0.25 multiplied to the first component is going to give us 1.099 times 10 to the negative 4. And then the second component is going to give us shear strain xy, and then it's going to be multiplied by 0.067. And then we bring this down. And this down. We can subtract this from both sides. And we can take, and when this is subtracted from both sides, we can take the shear strain and take that out. And so we could take out a negative shear strain. And so let's do this part first. So this gives us two point two, or sorry, 526 times 10 to the 4. And then if we take out that, we have 0.067 plus 0.433. We add these two together. We get 0.5. So 2.526 times 10 to the negative 4 equals negative 0.5 times shear strain. Divide both sides by the negative 0.5. And we get negative, let's see, 5.052 times 10 to the 4th, or the negative 4th. Yeah. And that's going to be in radians, because that's what the shear strain is in. Now that we have this, the shear strain, and we already have the shear or the strain of x, we can plug this into one of the two equations we had solved for the gauges, for gauge 2 and gauge 3. And so let's plug this into the first one that we solved for. And so we have 4.10048 times 10 to the negative 4 equals, we're solving for the strain of y now, so strain of y times 0.933 plus, we just got what the shear strain is, as negative 5.052 times 10 to the negative 4 multiplied by 0.25. We solve for this, and that gives us negative 1.263 times 10 to the negative 4. Subtract from this side, or add to this side, and then divide by 0.933 to get the strain of y. And that is going to give us 5.75 times 10 to the negative 4 inches per inches. Okay. Okay, so now that we've solved for this, we have solved for the state of strains, because we have strain of x that was given. We now have the strain of y, and we have the shear strain. So now we can move on. And the next step could be to do generalized Hooke's law. So let's go Hooke's law. Hooke's law says that, and Hooke's law is what helps us find the state of stresses. And so we just found the state of strains, and we can use those in order to find the stresses. And so it says that sigma x is equal to modulus of elasticity over 1 minus Poisson's squared times strain of x plus Poisson's times strain of y, I believe. And then for sigma y, it's going to start with the same thing, but the strain of x and strain of y are going to be switched. And so if we look in the appendix, we have appendix B, it says that E is equal to 10.1 psi. We can convert that into 10,100 ksi. And it tells us that G is equal to 3.7 psi. And that can also be converted into 3,700 ksi. The only thing that we aren't given is a Poisson's ratio for the aluminum alloy, and so we're going to have to solve for that, and we can use this equation right here, which is G equals E over 2 times 1 plus Poisson's ratio. These two can be switched, so it becomes, let's do it like this, E over G, and then 2 times 1 plus Poisson's ratio. And if we solve for it, it becomes this. 10,100 over 3,700. This whole thing is going to be divided by 2. That equals 1 plus this. And that gives us 1.36 equals 1 plus this, and then we subtract the 1 from both sides, and Poisson's ratio is going to be 0.36. Now we have the ratio, we can plug it into these equations with the strains that we just solved earlier from the Rosette. And so we have that, so I'm going to solve for these and just plug in the numbers. So our strain is going to be, I'm going to rewrite this. So the strain for x is a negative 150 times 10 to the negative 6, plus we have the ratio 0.36 times strain of y, which we solved as 575 times 10 to the negative 6. We can solve for the inside, and that will give us a result of, let's see, negative 150. And so this portion will give us 0.000057, and that's going to be multiplied this portion, which is 11,603.9. Multiply these two numbers, and we get a result of 0.66 ksi. And so that's our sigma x. Sigma y, we do the same thing. We already know since the beginning of both of the equations are the same, so we can use that number, 11,603.9. That's now going to be multiplied by 575 times 10 to the negative 6. Plus 0.36 times negative 150 times 10 to the negative 6. We can solve for the inside of this equation. This gives us 0.000521 multiplied by this. And sigma y equals 6.05 KSI. And so now that's given us the state of stresses. We can also solve for the shear stress of xy, because there's an equation that says shear stress of xy equals G times the shear strain of xy. Since we already know what xy is from what we solved previously, we have that shear of xy is negative 5.05 times 10 to the negative 4. But that can also be negative 505.2 times 10 to the negative 6. So I'm going to do that. So, and we have that G is from here 3,700 KSI from the appendix. So 3,700 KSI multiplied by negative 505.2 times 10 to the negative 6 radians. Solve that. That gives us an answer of negative 1.87 KSI. So now that we have the state of stresses, we can now go on to our next step, which is utilizing Moore's circle. In order to do Moore's circle, it helps us by finding the coordinates, and it helps us find the principal stresses, which is what we're looking for. So we have the shear and then the stresses down here. From the numbers we just got, we can create the coordinates, and the coordinates are going to be sigma x and then negative shear stress, and sigma y and positive shear stress. And so we plug in the numbers we got. 0.66, and then since this is negative, it's going to become positive. And we have 6.05 comma negative 1.87. We can plot these now on our coordinate system. So we have 0.66 and we have 1.87. So that's our first point. And our second point is 6.05, and it's goes to negative 1.87. And that's going to be right here. We can connect these to create a diameter. And in order to find the center of this point right here, we can do the average of these two numbers that we solved for xy and, or sorry, for sigma x and sigma y. And so that's going to give us 0.66 plus 6.05 over 2 equals 3.355 KSI. We can draw our circle using these points that we have found. And the next step is to find the radius. So we're gonna connect these points to create a triangle, and we can use this triangle to find the radius by using this distance, which is 1.87, and this distance, which is going to be 6.05 minus 3.355, which is equal to 2.695 to find it, and we use Pythagorean theorem, so we're going to do the square root of this distance squared plus 1.87 squared. Put that in the calculator to get an answer of 3.28 KSI for R. And we know from lecture that the max shear stress is going to be equal to our radius. And so the max shear stress is going to be 3.28. So that portion of the problem is solved. Now, in order to find the principal stresses, which are going to be here and here, sigma 1 and sigma 2, we can take from the Morse circle that we know, since we know the radius and we know the average stress, so we can take those two and we can take the average stress and add the radius to it in order to get this number for sigma 1, and for sigma 2 we can take the average stress and subtract the radius in order to get sigma 2, since it's past there. And so we go 3.355 minus, or plus 3.28. That's going to give us 6.635, I believe. Did I type that in right? Oh, yeah. And this one is going to be 3.355 minus 3.28. So 3.355 minus 3.28 equals 0.075 KSI. We have that for sigma 1, that for sigma 2, and that is our answer for the principal stresses. So we've gathered the principal stresses by finding the state of strains from the strain rosette, then using Hooke's law in order to find these answers for sigma x and sigma y and the shear stress, which are the state of stresses. And then we took the state of stresses, put them into coordinates into our Morse circle, and use those coordinates and the average and the radius from our circle in order to find the principal stresses of sigma 1 and sigma 2, which is 6.635 KSI and 0.075 KSI. This one would be the max and this one would be the minimum, and here's my signature.